So we all made it to now. Okay, so let me remind you what we had yesterday, because I was in the middle of the proof of the global existence of weak solutions, weak Leray-Hopf type solutions. So we had, okay, so the proof of okay, so we had our basic PDE, which I'll write here. So this is our basic PDE, okay, our approximate PDE here that we're dealing with, and we showed the following estimates for this PDE. Yesterday we showed that we have a global solution for fixed epsilon, okay, a strong solution for fixed epsilon, with the following uniform estimates with respect to epsilon. So U epsilon is bounded in L infinity in time locally, L2 in space locally, and it's equal to, it's a divergence free, intersect L2 in time H1 in space, and the dimension dependent estimate dt U epsilon bounded L infinity in time, L4 over n in time, H minus 1 in space. So with these estimates here, okay, we can use this estimate. So we have H1 locally, of course, compactly embedded in L2. Everything is local. Okay, and this is in H minus 1. Put local here. Okay, we have this compact embedding. So this gives us, using the Aubalion lemma, okay, this gives us, so here I'm using a slightly different version of Aubalion. It's not the same one. Yesterday I had L infinity, so I got C of 0t, and here I'm using L2, so I'm going to get compactness L2 in time locally, L2 in space. Everything is local. Okay? By Aubalion. I also get, because L2 can be compactly embedded into L2 with the weak topology. So this embedding here is just Banach-Alaoglu, okay? So because of that, I also get weak star, compactness L infinity in time, or C in time, into L2 with the weak topology. So L2 weak means L2 with the weak topology. What that means is that if you look at the integral of converging subsequence U epsilon times a test function in L2, that object is continuous in time. Okay? Okay. All right, so now passing to subsequences as needed. I have my sequence U epsilon. We can converge weakly to U. This is going to be weak L2 H1, weak star L infinity L2, and strongly L2, L2. Okay? So I can pass to this subsequence. Okay. In order to be able to use Abelian, I'm using the fact that dt epsilon is bounded in L4 over n into h minus 1. Okay? Okay. So this will allow me to pass to the limit in the weak formulation. So of course, this PDE star epsilon has a weak form. All you have to do is to multiply your PDE by a divergence-free vector field and put derivatives onto the test vector field. And so you get dt phi. So phi is some C-infinity compact supported function, divergence-free, a functional vector field. So I multiply the PDE by this, and I get j epsilon u epsilon d phi u epsilon equal to mu. I can put u epsilon Laplacian phi. This would be with a minus sign, actually. This, plus this minus. So again, there's a double integral here, minus the integral of phi 0 u naught epsilon. Okay, here we go. So now I send epsilon to 0, and what happens? Okay, this is a nice test function in any of these spaces that you want. So this term here will converge to this term. Here I have, if u epsilon converges weakly here, then j epsilon will converge in the same space. So here, and in fact, I'm using here the strong convergence L2, L2, because I have a quadratic nonlinearity. Okay? So because of the quadratic nonlinearity, j epsilon u epsilon will also converge to u in L2, L2 in time. This is a good test function for L2, L2 in time. So this term will converge to u d phi u. Okay? This term converges, of course, by linearity to nu Laplacian of phi. And here I have u naught epsilon is a convolution, so that converges strongly in L2, in particular weakly. So this also converges to phi naught u naught. Okay? Okay, so the weak form is satisfied. I have a weak solution. Okay? Okay, now what the difficult part here is the energy inequality. So this is the end of step 3. Step 4, energy inequality. So this was step 3. Step 2 were the uniform estimates. So step 4 is the energy inequality. And we start out from the energy inequality, the epsilon energy inequality. In fact, the epsilon energy equality, because my solutions for the epsilon PDE are smooth. Okay, so if I multiply by u epsilon, my PDE, my nonlinear term again goes away, because this is going to become ddt of u epsilon squared. This term here goes away. The p goes away because u epsilon is already divergence free, so the p goes away. Okay, and this is j epsilon u epsilon times the gradient of u epsilon squared over 2. So I get ultimately that ddt of 1/2 u epsilon L2 squared equal to minus nu integral gradient to epsilon squared, which is the L2 norm of the gradient. So this gives me u epsilon at time t L2 squared plus 2 nu integral from 0 to t gradient squared equals u epsilon naught L2 squared. So that's the starting point for the energy inequality. Okay. At this stage, the problem is that this converges in L2 in time and not L infinity in time, not C of 0t into L2. Okay, so I have to use this convergence in order to get an inequality which is valid for each time t. Okay, so how do I do that? So the difficulty or the issue okay. So how do I do that? I'm going to take a test function alpha, which is a test function in one real variable, okay, C infinity compact support in time, and I notice that, of course, alpha u epsilon will converge to alpha u also. Strongly L2. This is very easy to show. It's basically obvious, okay? And therefore, the L2 by weak convergence or weak lower semi-continuity of the norms, okay, I have that the norm, the L2 norm is bounded by the lim-inf of the L2 norms. Okay? This is just weak lower semi-continuity. And of course, I can square this, and this is still true. Okay? So what is this? This here is the lim-inf of this is so this is the integral from 0 to some capital T, or actually, I'm sorry, to plus infinity of the integral on Rn at this stage of alpha of t squared u epsilon tx squared dx dt. I can pull this alpha of t outside of this integral. It's only time dependent. Okay, and use the energy inequality for epsilon. Let me see if I can get this thing to work for me. Now, which one do I want down? This one. Okay. So this is less than or equal to, lim-inf is equal to the lim-inf as epsilon goes to 0, the integral of alpha squared t, and then I have an integral in Rn of the u epsilon of the u epsilon naught L2 squared minus 2 nu times another time integral. Sorry, what am I doing here? Just a sec. I'm missing something. Sorry. I want to add something. I forgot to add something. Okay. This is not good. Okay. I also have, on the same account, I also have that the gradient of u epsilon converges weakly to the gradient of u, weak L2, because u epsilon converges weakly to weakly in L2H1, okay? And therefore, again, I can put an alpha of t in front of this, and there will be, this will still hold true, which means that alpha squared, that the L2 norm of this L2 is less than or equal to, sorry, it should be like this. Is less than or equal to the limit as epsilon goes to 0 of the L2 norms of the gradient of U epsilon. Okay? Again, by weak lower semi-continuity. Okay. Therefore, and I can multiply everything new at no expense. And now I add these two. Okay? Okay, so now I add this with what's over there, the integral from 0 to t. Let's see. I think I have one guy too many. No, this is right. Sorry, I'm completely, okay. So add. And finally, I want to end up with the integral from 0 to plus infinity, the integral in x of alpha squared of t times tx squared plus the integral from 0 to t I know what I'm forgetting here. Sorry about that. I want this. This it. This goes here, and this goes here. I want to integrate this in time. Okay. So this plus the integral from 0 to plus infinity of alpha squared of t. I'm totally confused here. Just a sec. I'm missing. There's supposed to be 3 integrals in time here, and I've only got. So let's see. Tx. There it's okay. Yeah. No, this is right. This is right. The point is that for each fixed t, of course, this converges to this. So this integral here in time of this object here will be less than or equal to this. This is right.
It's a norm in space, not.
I'm sorry?
It's a norm in space only.
No, this is a norm in space and time. And sorry, this is an L2. I will multiply this by alpha of t. Okay, that doesn't do anything,
okay.
And then integrate in time. Okay, so this is right. So now it's this times the integral again from, and now it's going to be from 0 to some capital T of the integral in space, no more chalk. Integral in space, I'm going to put this up, of the gradient of U epsilon. This is supposed to be some ds, and this will be dt. So, which means that this is supposed to be, I think, yeah, okay. This is correct with t here and t. Okay, that's correct. So let me put this up a little bit so you can see. Can't put it too far up because otherwise I can't reach. All right, so what happened here? So this is less than or equal to the same thing with the limits integral now from 0 to infinity of the integral Rn. Now I should write this with norms to be a little clearer. This is going to be alpha squared of t times the L2 norm at time t. Plus, okay, plus the integral from 0 to plus infinity, 2 nu integral from 0 to t, or if you want, the L2, let me write this with the integral from 0 to t, it's better. This is at time s, L2 squared ds dt, times alpha squared. Okay, this is right. Okay, therefore, so the point is that the sum of these two things is going to be less than or equal to the lim inf as epsilon goes to 0 of the integral from 0 to plus infinity of alpha squared of t times u naught epsilon dt. I just multiplied by alpha squared of t and integrated. That's all I did. Okay? Okay, and this lim inf is equal to alpha squared times the L2 norm of u epsilon, just by dominated convergence. This converges to the L2 norm squared of u naught epsilon. This is it's a compactly supported C infinity function, so this is equal to the integral from 0 to t of alpha 0 to plus infinity of alpha squared of t u naught L2 squared dt. Okay, so that's true for any alpha which is C infinity compactly supported. So I'm going to choose a special alpha. So for any, so choose alpha C infinity compactly supported. So alpha such that alpha squared of t is 1 over epsilon, 1 over eta if you want, times, I'm running out of Greek letters here, rho theta of t minus t naught over rho. Okay, so it's going to be an approximate delta at t naught. Okay? And what I've just shown you is that putting everything together, I have, let me put things together. So for this alpha, what I have just shown you is that 1 over rho integral from 0 to plus infinity of theta of t minus t naught over rho times u of t L2 squared dt, okay, plus 1 over rho integral 0 to plus infinity theta t minus t naught over rho times 2 nu in the integral from 0 to lower score t gradient u s L2 squared ds dt. This is less than or equal to 1 over rho theta t minus t naught over rho times u naught L2 squared dt. Now we send delta we send the rho to 0. And what you get, in fact, you don't even need to do it with rho. Well, okay. Let's do it with rho plus. Okay, and what you get is that whenever T naught is a Lebesgue point, okay, of the L2 norm of U at time T, okay, you get U at T naught L2 squared plus the integral from 0 to T naught. This term is continuous. And this will converge to that. This term here is easy because you pull this guy out of the integral and you just get 1. State as a reasonable function, you just get 1. Okay? Okay. So this is true for all T naught Lebesgue points. Of the function U of S, L2 squared. Okay? Okay. The other points, so you already get almost everywhere. The energy inequality. Now, what do you do with the other points? For everybody else, for all other points, other times, use continuity in time with respect to L2 with a weak topology. And I will omit the details of this, but it's pretty straightforward. Okay, so I already have this here, and then I just want to show that I have the same thing using this continuity in time. Okay, so this means, just for those of you who don't know, this means that for every phi in L2 in X, you have the integral of U of T times phi. Well, this is U of T in X, of course. It's a continuous function. Okay? Okay. I'm not going to finish this. This is pretty easy to do. And then we have a bonus. Okay. Bonus at 5, which is that actually the initial data is attained strongly. So in the case of t equals 0, we have U of t converges to U naught strongly in L2. Okay. All right, so that's only at time t equals 0, and the proof of this is very easy. We know that U naught norm is actually equal to, I'm sorry, this is less or equal to U L2 squared. Exactly because U of t converges weakly to U naught in L2 as t goes to 0 because of the continuity in the weak topology. Okay? And this, of course, is less than or equal to the lim sup of the same thing, which this is by the energy inequality. This is less than or equal to the lim sup of U naught. Because the energy inequality now will tell me that this is always less than or equal to this. Okay, which is again, of course, L2 squared. Okay? And therefore, all the inequalities are equalities, and you get the strong convergence. Okay. So this finishes the proof of the existence. And, of course, this begs the question, what about uniqueness? Okay. And that's a big open problem in 3D again. Okay, partially solved by Maria Colombo, Dallas Albritton, and Elia Pruin. Maria Colombo will talk about this later this week, I think. Okay, but I want to make a few comments about uniqueness before her course. So first of all, n equals 2, as usual, is okay. N equals 3, open without forcing. Okay, so their result is that there exist forces for which you have non-unique solutions. Okay, but n equals, so I'm going to start talking about n equals 2, and then I will go to n equals 3. So theorem, if U0 belongs to L2 of R2, n equals 2, and U and V are Leray-Hopf weak solutions of Navier-Stokes with same initial data, then they're the same. Okay. Proof. So the critical thing here is exactly the difference between the estimate on the time derivative of U. In 2D, we know that dtu belongs to L2h minus 1. In 3D, all we know is that U belongs to L4 thirds in h minus 1. And that's the issue. That's the problem. Okay. So in 2D, we have dtu is minus U grad U minus gradient of pressure plus nu Laplacian U, and in 2D, dtu is in here, which means that I can test this against a function which is in L2H1. So allowed to, quote, multiply by U, which is L2H1. It's, quote, multiply because I'm taking the inner product, I'm integrating, so it's actually a pairing, a duality pairing here. But if I do the formal calculation for you, then that means that if I take W to be the difference, U minus V, and I look at the PD that's satisfied by W, okay, this is going to be the PD that the difference satisfies. For the same reason, I can multiply this by W and integrate. And what do I get? I get ddt 1/2 L2 norm squared of W. This term will go away. I don't have to worry about this. This is the term U dot grad norm W squared over 2. And U is divergence free, so that goes away. Plus the integral of W times W gradient to V equals minus nu gradient W L2 squared, and this term here goes away. Okay? Stop, come back. Okay, so therefore, we have ddt of the norm of W L2 squared is equal to minus 2 nu gradient W L2 squared minus, so I have minus WU dot grad V, and if I simply estimate this with gradient of V and L2 and WL2, W squared L2, which is WL4 squared. That's not going to be good. I need something to kill off the gradient of W, okay, and kill off the gradient of V. So what I'm going to do is write this as plus W dot grad W times V. I already put it on the right-hand side with a minus sign and integrated by parts. Okay, and so this now is less than or equal to minus 2 nu gradient W L2 squared plus W times V. So this gives me WL4, VL4, and gradient of WL2. Okay? Okay. Now I'm going to use Young. I'm going to put this here in L2 and this in L2. I think I'm doing something wrong. Let me double check. No, that's right. That's right. Okay. Actually, I don't need to do that yet. Sorry. Too early, too soon. Now I'm going to use Ledzinskaya inequality. Remember Ledzinskaya in 2 dimensions. That's the crucial estimate here. So this is n equals 2. Tells me that a function can be measured in L4 by its measure in L2 to the power 1/2 and the gradient L2 to the power 1/2. Okay. Therefore, I can measure this by minus 2 nu. I will keep the gradient L2 squared plus I'm going to get W L2 to the 1/2, V L2 to the 1/2, gradient of V L2 to the 1/2, and gradient of W L2 to the power 1 plus 1/2. So this is going to give me 3/2. Okay? Now I'm going to use the Young's inequality, raising this term to the power 4/3, and the term here to the power 4. Okay? And what I get is minus 2 nu gradient W L2 squared. That remains the same. This will give me WL2 squared, VL2 squared, gradient of VL2 squared, and gradient of WL2 squared, which I'm going to put a little parameter nu in front of it. So I'm going to get plus nu gradient W L2 squared, and there I got rid of the gradient of W. Okay, plus some constant over nu cubed, W L2 squared, V L2 squared, gradient of V L2 squared. And now I can throw away this term. Okay, so this is less than or equal to 0. And this term here, I'm going to call G of t. And it's given. Okay? Calling this guy G of t, and I'm calling WL2 squared Y of t. So with this notation, I have an ODE for the L2 norm of W squared, which says that Y prime is less than or equal to some constant Y times G of t. Now, the interesting fact about G is that it's integrable in time. So here you can use the ground wall inequality straight up and get y of t is less than or equal to y naught times the exponential of the integral of g. Okay, this is a finite number because v is L infinity L2 and L2 H1. So this is integrable in time and this is bounded. Okay, and y naught is 0. So y of t is less than or equal to 0, but y of t is a square of the L2 norm of w, so it's also greater or equal to 0, and therefore y of t is equal to 0. Which is what we wanted, so w is 0, and therefore you have uniqueness. Okay. What about 3D? What can we do in 3 dimensions? So the reason that I'm not allowed to do this in 3 dimensions is because I cannot multiply WT by W, okay? I don't have enough regularity in time. Therefore, what we can do instead, is what's called weak strong uniqueness. So definition, let U be a Leray-Hopf weak solution. Oops. Then U is strong if, so Leray-Hopf is L infinity L2, L2 H1. So you up this by 1 derivative. Okay? So if in addition to the usual estimates that you have for Leray-Hopf, you also have L infinity H1 intersect L2 H2. Okay. Notice that H2 of R3 is continuous, in particular bounded. Okay. Okay. And now notice that once I have a strong solution, I also have a better estimate for the time derivative. Because now my time derivative, is there anywhere that the PD is written down here? Way up there. Okay. Also, dtu, which is minus u grad u. Let me put the p's in front of here. What happens with this? If u is L2 H2, then Laplacian of u is L2 L2. So this term here is going to be L2 L2, just 2 derivatives. Okay. U is so the gradient of u is L2, L infinity L2. Okay, and u is L infinity. Okay. So this term here is also L2 L2. In fact, it's L2. It's L infinity L2. Okay. Fact. So in particular, this belongs to L2 L2. Of course, it's going to be L2H minus 1. Okay, so you have a better estimate for the time derivative of a strong solution. Okay. Okay. So with those observations, we can now write weak strong uniqueness theorem. And this states the following. So let U naught be someone in L2 sigma. This is in 3 dimensions. And U, a Leray-Hopf weak solution with initial data U naught. Okay. Assume, so assume there exists V, a strong solution with the same initial data. You know. Okay. Then U equals V. So for as long as so if you have a strong solution up until time capital T, okay, then the weak solution will coincide with the strong solution up until capital T, for as long as you have the strong solution. Okay? Okay. So again, let W is U minus V, and remember that we have the PD for W is this. And I want to put P's here because I don't want to have to deal with the pressure. Okay. Okay, and as we know, we cannot multiply by W, so we'll use the energy inequality instead. Okay. All right. So let's really look at what is WL2 squared. Okay. I want to look at this plus this. Let's look at what this is. Okay. Okay. So WL2 squared is U L2 squared plus V L2 squared minus 2 integral over R3 of U dotted with V. This is at time t. All of this is at time t. Let me erase this. Okay, plus this guy here. What is this? Gradient of WL2 squared. Again, I'm going to get the gradient of U L2 squared plus the gradient of V L2 squared minus 4 nu integral from 0 to t 3 of gradient of U, gradient of V. Okay? So let me keep this. Okay? Let me keep this for a moment. Since I'm going to put it up, it's going to be kept for a long moment. Oops. Of course, I went in the wrong direction. Stop. Now, I am allowed to multiply dtu by v, because my v belongs to L infinity h1, v is a strong solution, and dt belongs to L 4/3, h minus 1. So locally, it's L4 at h1. So it's a good test function. Okay. I am also allowed to multiply dtv by, because dtv, as we saw, belongs to L2, L2, so there's more than enough space to multiply by u, which belongs to L2, H1. Okay? And so this is what I'm going to do. I'm going to multiply. I'm going to write down what is the integral of dtu times v plus u times dtv, and use the fundamental theorem of calculus. Okay, so this object, on the one hand, okay, this is the time derivative of u times v, okay, and that's equal to u times v at time t minus u times v at time 0. Sorry. This is equal to the integral of u of t, v of t, dx. I'm sorry, I want to write this. There's an integral over here missing. So it's this minus the integral of u naught times v naught in R3, which is none other than the L2 norm squared of u naught. Okay? Okay, so what is this? On the other hand, so this on one hand. On the other hand, let's use the PDE. So this is the integral from 0 to t of the integral on R3 of minus u grad u times v plus nu Laplacian of u times v. The pressure term goes away, plus, for dTV, I'm going to write minus v grad v times u plus nu Laplacian of v times u. And let's integrate by parts. Okay, so who do I want to integrate one of these guys by parts. V dot grad U. I have to add and subtract something, yes. I want to add and subtract. What's this? V grad U dot V. Okay. All right, so what happens here? Okay, so this guy here becomes W grad U times V, okay? And this term here becomes V grad W times V, right? So this is going to be minus, in fact, minus W times V, and the other one is, then I need to do an integration by parts. Okay, I want to put this V dot grad onto V. Okay, so the other term, let's see, minus V dot grad V U from here minus V grad U V, term that I subtracted, plus the difference of, let's see, plus these guys. And what I said is I'm going to take this V dot grad and I'm going to put it onto V, and I get a minus sign, right? Plus sign. So this I'm going to trade V dot grad U times V. I'm going to make it V dot grad V times U with a plus sign. Just traded the V and the U, okay? And now I should have minus V dot grad W. So this is equal to minus W grad U times V minus V grad W, unless I'm doing something wrong. Yeah, I am doing something wrong. Just a sec. Minus V. This term went away. I did do something wrong. Wait a sec. It's easier if I copy this. Minus V grad U. Oh no, it is supposed to go away. Okay. It is supposed to go away. So, yeah, that goes away. Okay. Okay. So I finally have this. And what happened to my Laplacian term? Okay, good. So I've got this, and then I have this term here. I can put this derivative here. I'm going to get a minus nu grad U grad V, and here I get the same thing. So this is going to be minus 2 nu times grad U times gradient of V. Minus W grad times V, yes. Okay. So what have I found out? I have found out, so remember now, let me circle everybody here. So you know where I am. So I have this here is equal to this. Okay? In other words, what I found is I'm good. Okay, so what I found is that the integral of u at time t, v at time t, dx in R3 plus 2 nu integral 0 to t integral in R3 of gradient of u, gradient of v, dx ds, and I put this term on the other side. This is equal to the integral from 0 to t minus w grad u times v plus u naught L2 squared. Okay? Remember here I have this minus 2 u dot v minus 4 nu times this integral. So if I multiply everything by minus 2, I'm going to get a minus 2 here, a minus 4 here. Okay. Minus 2 here becomes 2 minus 2. Okay? And I'm going to stick this over there. Okay. Okay. So, so in the end I have w, I forgot to put equal signs here. W at time t, L2 squared. I simply wrote down, this is, the first line is equal to whatever's left over here. I simply forgot to write this. This plus 2 nu integral 0 to t grad w L2 squared. This is equal to the term u of t L2 squared plus 2 nu. That's less than or equal to u naught L2 squared. The second line is also less than or equal to the L2 norm of u naught squared. So I'm going to have less than or equal to u naught L2 squared plus u naught L2 squared. I'm doing this for emphasis. Okay, and then plus this last term, which I have just identified in this way. Okay, plus twice the integral in time of w grad u times v minus twice L2 squared. And again, I'm missing an integral in R3. Okay. Keep forgetting that integral. Okay. So guess what? This cancels with this, and we found this. And now I have to estimate this. This is what I have so far. Okay, I have this inequality here. And I want to put the, and I want to take this derivative here. Yes. And put it onto V. Okay. I think. Okay, and before I do that, I have to do something else. Okay, okay, so this is equal to, so I can add and subtract here. So this is this, right? It's W dot grad applied to U times V. And I can subtract off grad V from here, or if you want, W dot grad V times V, because this term, when you integrate, it's 0. Okay, this is the term which is W dot grad of V squared over 2. So this is the same thing as twice the integral in time, okay, now I'm good, of W grad W times V. Okay? Because I just added and subtracted the W dot grad V times V. And that's 0. All right. Now, I will need to use one more Gallardo inequality. Okay. I will want to put this guy here in L2, and this in L2, as usual. Okay. Except that now I'm not going to use the L4 inequality. I'm going to use the fact that V is a strong solution. Up until now, I've used the fact that V was L infinity H1. Now I'm going to use the fact that V is L2 H2. Okay? Estimate this by twice the integral from 0 to t of gradient W L2, gradient U L2, sorry, gradient V L infinity, UL2 V L infinity. Sorry, it should be a W. Okay. So I'm putting this in L2, W in L2, V in L infinity. V times W is L2. Okay? All right, and this is less than or equal to 2 nu. The L2 norm squared plus 2 over nu W L2 squared V L infinity squared. Okay? Okay. This term goes away. This goes away with this. And I finally have the L2 norm of W squared less than or equal to the integral in time of the L2 norm of W squared times VL infinity. Okay. And now I need one more Gallardo here in inequality, which states that the L infinity norm of a function can be estimated by the L2 norm times the L2 norm of the Laplacian. And the exponents are this in dimension 3. Sorry, this should be 3/4. Okay? And now I'm home free because this is the square, so this is going to be, so dt, sorry, not ddt, w L2 squared is less than or equal to the integral in time of w of s L2 squared times v L2 to the 1/2 times the Laplacian of v, there's something wrong. Shouldn't be 3/2. No, yes, sorry, it is correct. Okay, this is correct. Okay, so we've got this. Now, let's look at this object here, okay? This object here is variable in time, and that's the last step, okay? So I'm going to look at this object here. I'm calling this object g of s, okay? And I'll now show you the last step, which is that g of s is integrable. Come back. Stop. Okay. The integral of g of s, is the integral from 0 to t v L2 to the 1/2 Laplacian of v L2 to the 3/2. Why is this integrable? Because if I put this guy here in L4/3, and this, in fact, yeah, it's okay, in L4, okay, then this is less than or equal to the L4 norm of this term is going to involve taking this and raising it to the 4th power, which gives me the integral in time of v L2 squared, which is finite, because this is even L infinity h1 raised to the power, what is this going to be? Squared. Sorry, it's this to the power 1/4, which is just the L2 norm to the power 1/2 times the integral from 0 to t of the Laplacian of v L2 squared. When I raise this to the power 4/3, I get L2 squared to the power 3/4, and this is finite because v belongs to L2 H2, and this is finite because v belongs to L infinity H1. Okay. So this is integrable in time. So now I'm in a situation where I have a similar Grunwald inequality to use, except in integral form instead of differential form. And these are a little trickier, but it's also okay. So if I have y of t equals to w of t L2 squared, what I've just shown you is that y times t is less than or equal to the integral from 0 to t of y times s at time s times g of s, and the integral from 0 to t of g of s ds is finite for all t. Okay. So this implies y times t is less than or equal to y naught times the exponential of this integral. And then this is 0, so then y is 0. Okay? Okay. All right. So there's a generalization. Oops. Yeah, that's it. So there is a generalization, which is called the Prodi-Serrin uniqueness criteria. Okay. And it goes like this. It's no longer strong uniqueness, it's just a criterion for uniqueness. Theorem. Prodi-Serrin. It says that U and V be Leray-Hopf weak solutions with the same initial data. L2 sigma, okay? And assume that you know that V belongs to LP in time, LQ in space, with 2 over P plus 3 over Q equals 1. Then U equals V. For as long as V belongs to LP in time, LQ in space. Okay. I'm not going to prove this theorem, but the proof is just exactly the same proof that I just gave for the weak strong uniqueness, except just noting that this condition here, LP in time, LQ in space, 2 over P plus 3 over Q equals 1, is exactly what you need to make the proof work. Okay, so instead of using these Sobolev estimates, these Gallardo-Nirenberg, et cetera, you're going to use just these LP, LQ estimates and a lot of Holder inequalities. But it's exactly the same proof. There's no new idea. Okay? All right. A word about these exponents and a word about why we care so much about uniqueness. So, first of all, note. Okay? First of all, if V is a Leray-Hopf weak solution, which belongs to LP in time, LQ in space, then V is a strong solution. That's the first observation. Okay, so this gives you additional regularity. From the fact that it's unique, it's Prodi-Serrin, then you have regularity. How do you show this? You use the vorticity equation. Okay? So what I need to show is that the H1 norm is bounded and that it's L2, H2. How do you show the H1 norm is bounded? You look at the vorticity equation and you multiply by W and show, by omega, and show that the L2 norm does not blow up. The estimates are such that you show. So the proof is you look at you multiply by omega, integrate, and you show that the LP, LQ, that you use Holder's inequality ad infinitum to show that the L2 norm is bounded. once you know the L2 norm of the vorticity is bounded, okay, then you go back here and use parabolic regularity to show that the gradient of omega is integrable in L2, L2. All right, once you know that omega is bounded in L2, that gives you, by elliptic regularity, that gives you that U belongs to L infinity H1. So this estimate here implies U is L, not U, V. L infinity H1, and this estimate here, again by elliptic regularity, gives you V is L2 H2. Okay? So you use the vorticity equation again. So in other words, uniqueness and regularity are intimately tied. Okay, so it's a very relevant question, the issue of uniqueness. Okay. One last word about Navier-Stokes in 3D before I very quickly move to 2D weak solutions. I'm going to do this really at jet speed here, which is this. What is the relevance of these exponents? Okay. To understand this, we need to understand the scaling, the natural scaling for Navier-Stokes. So suppose I have a solution U. Let me put P's here. Okay. And suppose I want to rescale it. So I'm going to write V lambda to be lambda to some power A U of lambda to another power times T, and lambda to a third power times x. Suppose I want to ask myself what are A, B, and C, so that if I stick this into the equation, V lambda satisfies Navier-Stokes. Okay, for all lambdas, for all values of lambda. And this happens when you take the time derivative, you're going to get lambda to the A plus B. So I need the exponent A plus B. So I want this to solve Navier-Stokes for all lambda. So I need the exponent A plus B to match the exponent that comes in here to match the exponent that comes in here. The exponent that comes in here is going to be lambda to the A times lambda to the A times one derivative of U, which is lambda to the C. So I need this to be equal to 2A plus C. And the exponent of lambda that comes when I take this guy is going to be lambda to the A, and then I have two derivatives with respect to x. So I'm going to have A plus 2C. Okay. When you solve this, from here you're going to get A equals C. Okay, you stick this in here. A plus B has to be equal to 2A plus C. This is equal to 3C. This is equal to just B plus C. You're going to get B equals to 2C and A equals C. So I just call lambda to the C a new parameter mu, and bottom line I have V lambda is going to be lambda U of lambda squared T lambda X. Okay? Okay, now we want to notice the following thing. Okay, what is the LP? What is P? So that the LP norm is constant, is independent of lambda. Well, it depends only on lambda squared T. It's a function of lambda squared. So you still have this guy here. What is the LP norm? And the answer is P equals N. Okay. P equals N. This will make the norm not invariant, but depending only on lambda t. When you compute this to the power n, you get lambda to the n, u to the n, and you're going to get lambda x. U to the n of lambda x. You change variables, your lambda to the n is exactly your Jacobian here, okay? And therefore, you need p equals to n. Okay? All right, that means that p equals 2 in R2 is a good space for you to start. But in R3, you would need to be starting with L3 initial data. Okay, and actually there is a result on L3 initial data. As long as the data is sufficiently small, you get a strong solution of what's called a mild solution. Okay, this is a result due to Kato. But part of the problem in 3D is that Navier-Stokes in 3D has the wrong scaling, okay, for us to have a good 3D theory. Okay, I basically ran out of time. I don't think in 2 minutes I can work out. If I had 5 minutes, I could do Yudovich, but not in 2 minutes. So
You have 5.
I have time?
You have 5 minutes, yes.
I have 5 minutes?
Yes.
Okay, then let's do Yudovich. Okay, good. Problem is all this up and down with the board. Oops. Okay. All right. So we learned that 3D Navier-Stokes and 3D Euler are complicated, but 2D is much simpler and much more amenable to analysis. 2D Euler and Navier-Stokes. All right. So the first thing that we learn is that we have weak solutions to Navier-Stokes in 3D, but we know nothing about weak solutions to Euler in 3D. And the situation in 2D is completely different. Okay? So in 2D, we are allowed to study Euler solutions to Euler equations with irregular initial data. So I want to study, so the reason that we can do this is because we have a good vorticity equation. So in 2D, we have this 2D vorticity equation. Omega is a scalar now, okay, and it satisfies this nice transport equation. Okay. And one of the things by an incompressible flow U, and what this means in particular is that if omega naught is an LP of R2, then omega at time t will also be an LP of R2. This as long as omega is smooth, that's true, that's an easy calculation. Okay, so it motivates the study of weak solutions with LP vorticity. So the first result that I want to mention is the following theorem. This, although it's an easy theorem, it's relatively recent. 87, I think. Something like that. Okay. It's due to Rondapurna and Andy Majda. Okay. 1987, and it says this: let omega naught be in LP. If we're in the full space, we need a little more control than just LP. Then there exists a weak solution to 2D Euler for P's if P is bigger than 1. You also have a solution if p is equal to 1, but the proof of that is much more complicated, and I don't want to get into it today. Okay? So let me show you in 2 lines how the proof of this goes. You start by mollifying initial data. Take u naught epsilon, mollification of some u naught. You take omega naught epsilon, mollification of omega naught. Okay? Actually, what you want to do is you want to take initial vorticity and build your initial velocity from your initial vorticity. You can do that by solving that elliptic system in a sort of a standard way. Okay, now this guy here is smooth. And it's still LP, and it's still L1. Okay? Okay, so since this guy is smooth, we can solve exactly to the Euler and generate a solution u epsilon and a solution with vorticity omega epsilon with initial data u naught epsilon omega naught epsilon. Another possibility is solve 2D Navier-Stokes with initial data u naught omega naught or u naught epsilon omega naught epsilon. Whatever works. I mean, both of them work, is what I mean. Okay. And then from this, you're going to get u bounded. Well, actually it's WP star, but I'm cheating a little bit here. There's a slight problem at infinity, and I want to forget about this problem at infinity here. Okay? So it's W1P log for sure. Okay? Which means, this is U epsilon, which means that U epsilon, you're going to get this, you're going to get this bounded in, so the time derivative will be bounded into some negative Sobolev space. I don't want to make very precise which Sobolev space. So in the end, I get U epsilon is going to be compact, continuous in time, L2 in space. Okay. Because if p is greater than 1, W1P is compactly embedded in L2 in the plane. Okay. And that's all done. QED, once you have compactness here, you can pass through the limit in the nonlinear terms, and you have a weak solution. Okay, so QED. Okay. In particular, this gives me existence of a weak solution in L infinity. Okay, so in particular, if omega naught it belongs to L infinity, I have a weak solution. Now, this is not the best way to construct this weak solution. Okay, the best way is by means of transport characteristics. Because, for instance, this proof does not give me any information on the structure of my weak solution. I don't know what it looks like. Okay? There is another way, but that one is more time-consuming. Okay? So if p equals infinity, can show there exists particle trajectories. In other words, there exists a Lagrangian description and the vorticity is constant along these trajectories. Can only do this in the case p equal infinity. That we have a Lagrangian description of the flow, like that. Okay. However, there's one more thing that you can do in infinity is theorem, and this was Yudovich's PhD thesis from 1961. Okay, published in Russian. published in English in 1963. Okay? There exists a unique weak solution if omega naught is L infinity. And I want to just show you what's the idea. Okay? Yeah. I'm sorry? Yes. The proof comes from the elliptic regularity estimate. Okay, so d squared f LP is bounded by, we all know that this is true, Calderon-Zygmunt inequality for p greater than 1, okay, with a constant here which is linear with respect to p. That's the key fact, is that the Calderon-Zygmunt inequality has a bound which is linear with respect to p. And so what you do is you look at u minus v. So suppose you have two solutions. You look at ddt of the L2 norm. We've done this calculation a zillion times. Okay, now I no longer have viscosity here. Okay, so this is going to be equal to minus the integral of w grad u. Okay. And the idea is to take my gradient of one of these solutions, doesn't matter which one of these guys here. This is going to be L infinity. This is not going to be L infinity. The vorticity is L infinity. The Calderon-Zygmunt inequality doesn't work very well in L infinity, but I will estimate this in LP, okay, for any p. And so we finish up with this. L where do I want this? Sorry about that. VP grad U2. Yes. P prime to the 1 over P prime. This is square. So it's this guy here times grad U LP. And I put a P here. Okay? And this is omega L2P prime, WL2P prime, I'm sorry, raised to the power 2P prime minus P, minus 2, sorry. Okay? Okay. So, in fact, get this. Just a sec. I need to have L2 squared here. I put something wrong. Did something wrong here. Okay. Do this too fast. Okay. So one of these guys I put in L2 and the other in L whatever. No, okay. Okay. Etc. Less than or equal to, what's the bottom line here? Oh, sorry about that. This is the velocity. Okay. So this guy becomes, this is LP prime. Just like so. And then finally, what we get is P, there's a constant here, CP, this is not omega, that's why it's a W. Messing up here, this is W. Okay, so finally, I wind up with this. Okay, so I'm going to get an L2 here, 2 over P prime, and omega L infinity to the 2p prime minus 1. Okay. All right, there's a bunch of calculations in between. The bottom line is when you integrate this, okay, when you integrate this, p prime is a Lebesgue exponent. So this gives me, after you do Gronwall, this is going to give me c t to the 1 minus 1 over p. P greater than 1. Okay, so this is going to be a positive exponent for any p greater than 1, and I just take t small. Okay, and then I send p to infinity. Okay, that's it. All right. Okay, and in the end, you show that over a small time period, w is 0. Okay, then you start over. From here on, the time period is it does not depend on initial date. It doesn't depend on anything. Again, the time period is small, is less than 1. So you're going to get w is 0 on this new time period, and so on and so forth, and w is 0 everywhere. Okay, this I messed up totally, and I could give you my notes later. Okay, in the notes it's right here as well. Okay, thank you, and sorry for messing up the end.